Hi, and welcome to our presentation. The motivation behind our work origined in two computer viruses from 2017, namely WannaCry and NotPetya. Together, these two created an estimated damage of $14 billion worldwide in several different corporations and also different countries all over the world. So this was a tremendous damage that was done. One reason why they were so particularly harmful was their way of dissemination. They both were self-propagating malware, and what led to their self-propagating behavior was a certain vulnerability in a networking protocol. So they were able to actually self-propagate without the other computer on the network to actively participate in this. Now let's have a closer look on how this proceeded in general. We have here an example network, and on this example network there is an initial infection coming from the internet that infects the first host. And this infected host then starts to infect other hosts by sending the same network packages all over again. And after a while, this first computer shows some sign of infection. This, in that case, is a ransom note. But at the time the first ransom note is shown, many other PCs on the network could already have been infected. And other infected hosts operate the same way, so after a while the whole network is infected if it is vulnerable to this vulnerability. Now, for a human defender, this can be a very challenging task, because if we assume a human defender now tries to isolate infected hosts, the human defender would need to constantly check the network traffic, because if he or she only operated after the sign of infection is shown, then the operator would always be one step behind, because there are already more computers infected than it is actually shown. So we again end up here with a network that is completely infected. On the other hand, what would be the optimal solution here? The optimal solution here, given that there is we cannot prevent the initial infection, is that we have some sort of agent or bot that recognizes the self-propagating behavior of the first infected computer, and then automatically keeps track of the network traffic, and not only tries to isolate the first infected machine, but also all other machines that were communicating to this machine. And so we end up with a network that is only partially infected, but the rest of the network is at least safe. Now, how can we create such a bot, or how can we train such an agent? Back when I started with the work, the go-to approach here would be supervised learning, which would mean that we would need a huge load of labeled data, especially network packets, and this then would mean we would then create a model with this labeled data that classifies network packets in different classes, and according to these classes, when they appear, we just use some hard-coded prevention mechanisms that help the network in the end. And the downside of this approach is that we need a lot of labeled data, and since data usually does not come labeled by itself, somebody needs to make these labels. And because this labeled data is scarce, it is very valuable, and also I'm kind of lazy, so I didn't want to label this myself. So I was looking for different approaches, and that's where reinforcement learning came into play. reinforcement learning, we provide the agent with an environment, let's say a network environment that is not very valuable to us, and we give the agent a little bit of control over some actions. In that case, it's actions to cut network connections to individual machines. And then we let it play some episodes, and after an episode is finished, we give it a reward, how good it has achieved its goal. And after a while, it starts experimenting, and sometime it gets some partial solutions like this one here. And it also should learn to not intervene in episodes where no infection actually happens, because this is also bad, because we want a performing network. And in the optimal way, after a while, it learns to behave optimal, and in episodes where there are infections, and also it starts behaving optimal in episodes where there are no infections. Now, so much to our goals and the theory, but it's usually when it comes to practice where the problems begin. Now let's have a look what we actually created. We set up a little environment, a little test environment network, where we had 4 virtual machines, which were connected, as you can see on the right side here. And these virtual machines consisted of 3 vulnerable virtual machines, which were running Windows operating system and were vulnerable to the same vulnerability, and an agent virtual machine which was running on Linux to make sure that this is not vulnerable to this vulnerability. And we wanted to use virtual machines because we wanted to keep this environment as close to reality as possible. And using virtual machines enabled us to use real software, real operating systems, which creates real network traffic. We wouldn't have to emulate or simulate. And also we could use real malware, in our case NotPetya, which also enabled us, the virtual machines, to revert damage done by the malware via snapshots at the end of an episode. So this was a huge upside. The downside, on the other hand, was that we had to play this out in real time, and reinforcement learning is not known to be very efficient. So we knew that we needed to play a lot of episodes here for the agent to learn, and especially when we didn't know whether this was feasible or not, we had to experiment quite much. So playing it out in real time would take us a lot of time. So we adapted the setup, not the setup actually, but the focus of the agent a little bit, so that we could replay this in faster than real time. And we set the focus of the agent to only a single network connection. We also set an episode to 10 minutes, and the agent had the ability to interact with the environment every second. And the vulnerable virtual machine would be infected at a random point in time. And the goal of the agent would be then to cut the connection as quickly as possible after an infection has happened, and only after an infection has happened. So let's have a look at the action space. The action space therefore is fairly simple because it only consists of 2 actions. One continue action that continues as it was, and one connection that cuts this single network connection. This setup enabled us to record episodes of the whole environment with all virtual machines without any intervention. So there is an infection, and malicious network packets are recorded as is. And when we replay this, if the agent chooses the action continue, then the packets are replayed as they are. But If the agent chooses the cut action, then further network packets are blocked or discarded, and yeah, we can therefore replay this faster than real time. Also notice that the agent cannot cut a connection twice, and therefore if the connection was once cut, the agent would remain in the same state for the rest of the episode where no packets are received or sent. So because this has no semantical value, we decided to end the episode as soon as the agent chose the action cut. Now, some sort of flow diagram of the environment could look like this. The agent starts in a certain state S1 and can choose between cut and continue. If it chooses cut, then it ends in a terminal state, and if it chooses continue, it gets into the next state, S2, and so on and so forth. Now, one might wonder that this is very similar to supervised learning, and it kind of is, I have to admit, but there are several distinctions, I would say, or benefits. One is that in the future, one can adapt this approach with additional actions, and therefore this would not be comparable to supervised learning then anymore. And on the other hand, we also got rid of the necessity of the label, which is a great benefit actually, because now we have an environment that gives rewards instead of someone has to sit down and label each and every single network packet. So let's get into a little bit more detail here. Let's have a closer look at the reward function. The reward function is a function of 3 parameters. The first parameter I is the time step where the infection happens. The second parameter T is the current time step. And the third parameter is the action the agent has chosen. In the case of the continue action, the reward is fairly simple. It is simply 0 if the agent performed this action within an episode. So if the current time step is smaller than the terminal time step, which in our case is 600 because 10 minutes times 60 seconds per minute equals 600. And only in the last state, if the agent chose the continue action, it's either a 1 or -1 depending on whether there was an infection within the episode or not. A little bit more interesting is the reward for the cut action. This reward is -1 if the action cut was chosen before there was an actual infection, and it is 1 divided by t minus I if it is chosen after an infection. And this is a little bit better displayed in this graph over here. The blue dots are the reward function, and the purple bar is the time step of infection. Also note that the agent gets a reward of -1 at exactly the time step of infection, because this was only a lucky guess, because the agent couldn't have seen any signs of infection at that time. Now, the state space is a very high-dimensional one-hot encoded vector. I won't go too much into detail here due to time restrictions, but you can see that this is a very large one-hot encoded vector, and the state is then a sum of these one-hot encoded vectors. The agent that we used finally has a function approximation of k-nearest neighbors algorithm. We used the learning algorithms SAS and Q-learning, and also had a hyperparameter search. You see here in bold the best performing hyperparameters. And the results, coming to the results, we had a data set of 20 recorded episodes, and we split this in training and test set. And what we can observe from the graph is that our agent learns. It does not learn perfectly, but it's still learning, and that's what this work is to us, a feasibility study, whether this is actually possible or not. So to summarize, what we have shown is that we created an agent that can identify when a computer starts spreading self-propagating malware, in this particular instance NotPetya, and then contain it. This is learned via trial and error learning and does not require any labels. To differentiate, what we have not shown in this work is there is no generalization to only self-propagating behavior. So in this instance, this could have been due to NotPetya. And we also were focusing only on one interface instead of multiple interfaces at the same time, but we are positive that this can be easily extended. So if you have now any questions to my work, please ask me. I'll be happy to answer, or I'll refer to the paper. And otherwise, thank you for your attention.